Throughout all history, most nations have found the seas to be barriers to military operations. But those few nations that have developed naval power consider them to be an asset. Today, the United States Navy is the most powerful naval force in the world. To maintain that superiority requires constant effort along a broad front of activity. Basic to that effort is a continuous expansion of our knowledge of the oceans. Such knowledge is difficult to obtain, but fortunately, it pays double dividends. Eventually, it will enable man to exploit the vast resources that are locked within these waters and the land beneath them. For within its almost limitless domain, scientists see an expanding supply of food for the teeming populations of tomorrow and a virtually inexhaustible supply of minerals and metals to be exploited when advancement in technology makes it commercially feasible. A major element of the Navy's research program is focused upon the land that lies beneath the sea. No one knows how or when it all began, but many believe there was a time in the distant past when the molten earth froze into the form similar to that which exists today. Rains fell for millions of years, filling the low places that are the great ocean basins. No one knows what the continents looked like then, but there's one thing that's known for certain. They differed greatly from what they are today. For the ensuing billions of years, forces of nature have been at work, changing the shape and features of the land. Most of the water that falls upon the land eventually flows into the sea, carrying part of the land with it. Glaciers pick up part of the land, carry it to sea in icebergs, and drop it where the ice melts. Winds pick up dust and sand and drop them into the sea. Waves beating against shorelines eat them away. Water movement caused by storms, tides, and currents moves solid earth particles from place to place. As the earth cooled over millions of years, enormous pressures upon its crust have caused faulting, folding, buckling, distortion of the land, often slowly, but sometimes suddenly. Molten lava from thousands of volcanoes over geologic time have formed hills and peaks, even mountains. Under the seas, these changes are as extensive and are of the same type as on land. This hidden land has always been difficult to measure, to sample, to observe. The accumulation of knowledge has been slow. In recent years, improvements in instruments and techniques have made marine geological studies more rapid and precise. The precision depth recorder plots a continuous record of depth as a ship moves at normal speed. The deep sea camera brings back photographs of the ocean floor from depths of nearly 36,000 feet. The deep sea corer obtains cores more than 100 feet long from the ocean floor. And most dramatic, new deep submersibles carry men to the deepest parts of the oceans to observe and to photograph. A knowledge of this land, even though it is incomplete, is essential for greater economic exploitation of the seas and for national defense. The portion of the oceans adjacent to the continents are better known than any other. No other part of the ocean attracts as many people. Here, a man can establish close communion with the forces of nature. No other part is as hazardous to shipping. It's the portion that's most subject to change. So its rocks, reefs, shoals, tides, and currents have been the most accurately charted. Buoys and lighthouses warn of dangers and help navigators guide their ships along safe channels. Great fish populations seem to prefer to live in these shallow waters. Here are caught millions of tons of fish annually. For thousands, a livelihood. For millions, an important source of protein. To some nations, ocean fishing is so important an industry that they have claimed exclusive fishing rights far out to sea, sometimes for hundreds of miles. To others, undersea oil reserves and mineral deposits are of similar importance. For example, in 1948, the United States claimed oil and mineral rights out from our shores to a water depth of 600 feet. Outward from the shores of the continents, the land slopes gently downward, usually several miles, to a point where there is a marked increase in slope to greater depths. Worldwide, this break in slope comes at an average depth of about 430 feet. Deposited on these continental shelves is sedimentary material that has been eroded from the land. Ancient riverbeds meander across these shelves, and ancient beaches have been found at the edge of the shelf, evidence that they were once part of the land during periods of low sea level. The continental shelf varies greatly in width, as can be seen along our east coast. 275 miles at Massachusetts, 90 miles at New Jersey, becomes narrower at Cape Hatteras, then widens to 60 miles at northern Florida, and disappears at the east coast of southern Florida. Where rivers flow into quiet areas of the ocean, deltas are built up, in some cases on the shelf, in others they form the shelf. These shelves vary greatly in profile. From Boston, there's a downward slope for about 35 miles, a sand ridge at Stellwagen Bank, a series of basins and troughs for the next 160 miles, and another rise at George's Bank, which itself is about 100 miles wide. At New Jersey, the bottom is rough, but the slope is consistent and gradual. At Jacksonville, Florida, it smooths out. The shelf area is of great significance to naval planners because it is here that two major operations of naval warfare take place. Mine warfare, which includes both mine laying and mine sweeping, and amphibious operations. For transporting men and equipment from ship to shore, landing craft must have an unobstructed passage right up to the beach. And the beach sand must be sufficiently compacted to hold the weight of the heavy equipment. Tentative operational plans can be prepared from charts that show depths, bottom conditions, and tides based upon the best information available. But waves frequently build, destroy, and shift sandbars and beaches. So before finalizing plans, up-to-date intelligence must be obtained of the beach and the sea approaches. One major element in planning minefields is predicting the effectiveness of individual mines. Upon impact, they may penetrate into the bottom or gradually sink over a period of time. The degree of burial depends upon the type of bottom sediment and the strength of surf or current. For most mines, a moderately firm, slightly rough surface is best, such as coarse sand or a mixture of sand and gravel. In a soft mud bottom, bottom mines may become so deeply buried that most of their effectiveness is lost. Buried mines are extremely difficult to sweep. If the bottom is hard and smooth, the mine may roll, become displaced and possibly damaged. But for moored mines, the anchor holds more firmly if it does sink. So here, a soft bottom is better. In sheltered harbors, bays, and estuaries, most of the bottom is mud. Outside the bays, most of the bottom sediment is sand, but large areas of gravel and mud are found. Rocks and rock bottom are frequently found off rugged portions of the coast. This information is furnished to the naval planner in the form of bottom sediment charts. At the outer edge of the continental shelf, the land plunges downward 2 to 3 miles to the ocean bottom, forming the walls of the great ocean basins. The slopes are frequently cut by ravines and canyons, sometimes 2,000 to 4,000 feet deep. Some canyons are continuations of existing rivers that once flowed across the shelf when it was above sea level. Others may have been formed by turbidity currents whose movements were triggered by earthquakes or by various combinations of causes. Continental slopes are usually unbroken in their descent, or almost so, with perhaps only an occasional slight interruption. But a few slopes have terraces like the Blake Plateau. East of Cape Kennedy, Florida, the slope is interrupted at about 3,000 feet by this plateau, which extends some 150 miles before the final plunge to the bottom. Other slopes are interrupted by mountain ridges and peaks. For example, west of Los Angeles are the islands of Santa Catalina, San Clemente, and Santa Cruz, all peaks some 8,000 feet above the ocean floor. If the sea level were lowered by about 3,500 feet, the mountain ridges would contain several lakes as deep as 4,000 feet, up to 20 miles wide and 80 miles long. The sediments deposited upon continental slopes vary greatly, but worldwide they average about 60% mud, 25% sand, 10% rock and gravel, and 5% shells and ooze. These photographs were taken in 8,000 feet of water along the Atlantic slope east of Massachusetts. Here in 1963, the submarine Thresher went down. In searching for her remains, hundreds of bottom photographs were taken, and this became the most intensively photographed slope area in the world. The deep ocean floor begins at the foot of the continental slope, some 12,000 feet down. Here, the landscape is as varied as on land. In this domain of perpetual darkness, topographic features formed millions of years ago have changed very slowly. Here, there is no wind, rain, or frost to erode them. In the Atlantic, the most prominent feature is the greatest mountain range on Earth, the Mid-Atlantic Ridge. Rising near Iceland, it extends southward for 10,000 miles at a height of 5,000 to 10,000 feet above the ocean floor. It lies almost exactly midway between South America and Africa, leading some geologists to suggest that at some time in the distant past, the two continents were joined, and that they broke apart, leaving a crack where the ridge was formed while the continents drifted to their present positions. Occasionally, pinnacles poke above sea level as islands. The Azores, Ascension, and Tristan Da Cunha. At about 50 degrees south latitude, the ridge turns sharply eastward around the tip of Africa and continues toward the Indian Ocean. A mighty rift, up to 30 miles wide, slits the ridge's crest along its entire length. It is along this ridge that most of the earthquakes in the Atlantic occur. At the base of the ridge are bumpy stretches called abyssal hills, which level off into flat, smooth abyssal plains, some 3 miles below sea level. Throughout the Atlantic are hundreds of peaks called seamounts that rise thousands of feet above the ocean floor. Many are of volcanic origin. Under land, the Earth's crust is 25 to 35 miles thick and is primarily granite. But under the sea, it thins down to some 3 to 8 miles and is primarily basalt, a dark, fine-grained igneous rock denser than granite. On top of this basaltic crust lies several thousand feet of sediment, materials that have remained undisturbed for millions of years, a record of geological history. Most of it is debris that has rained down over eons of time, imperishable remains of marine life. The Pacific Ocean is the biggest single feature of the Earth's surface, bigger than all 6 continents. Half of all the water on Earth is here. It is almost completely surrounded by lands that are volcanically active. In fact, the volcanoes along its rim are so numerous that they are sometimes referred to collectively as a ring of fire. Its numerous islands are but visible evidence of volcanic eruptions that have occurred innumerable times over geologic history beneath its deep waters. The Hawaiian Islands are all volcanic peaks along a ridge formed by volcanic material being forced upward through a break in the Earth's crust. The Aleutian Islands are peaks along a curved mountain ridge that extends some 1,800 miles from the Alaskan mainland. However, this ridge was formed by an upward buckling of the Earth's crust, and the volcanic peaks were formed after the ridge was built. Scattered throughout the entire Pacific Ocean are many mountain ridges and hundreds of seamounts, round-topped volcanic peaks. Some of these peaks are flat-topped and are called guyots. Why flat-topped? Nobody knows. One explanation is that once their rounded peaks extended above the surface as islands. While thus exposed, they were flattened by erosion. Then, over eons of time, the ocean floor sank. Possibly during this time, the sea level rose. Now most of these platforms are found at depths of 3,000 to 5,000 feet. A few are scattered at random, but most appear along 3 lines, one extending south of the Kamchatka Peninsula, another in the Marcus Necker Rise west of Hawaii, and the third in a zone between the Marianas and Marshall Islands. One particularly interesting feature of the Pacific is its dozen or so deep trenches, the greatest depths on Earth, all over 25,000 feet deep. They appear intermittently almost around the entire rim of the ocean. They are all alongside curved mountain ridges on the side away from the nearest land. Numerous volcanoes appear along these ridges. There are more earthquakes near them than in any other equal area in the world, indicating that faults lie underneath. These almost always have origins at a shallow depth. Toward the shore, earthquakes have origins at increasing depth, indicating that the fault line gets deeper. Possibly these trenches were all formed by a folding or distortion of the Earth's crust. Here are photographs of the deepest place on Earth, the floor of the Marianas Trench at its deepest point, 35,700 feet. These were taken in 1960 by Dr. Jacques Picard and Navy Lieutenant Don Walsh in the Bathyscaphe, Trieste. Another interesting feature in the Pacific is the hundreds of coral reefs and atolls found in the tropical areas. Most coral reefs are built up by the skeletal remains of small animals that grow in vast colonies. For maximum growth, they need plenty of light, so they are usually found in clear, warm water and at shallow depth. Fringing reefs grow out directly from the coasts of many islands with scarcely a break, sometimes for many miles. Barrier reefs are separated from a coastline by a lagoon channel. A typical one lies off Papeete Harbor, Tahiti. Atolls are reefs that extend above sea level and enclose a circular lagoon. An amazing feature of atolls is the thickness of the coral. On Enewetak, for example, it is over 4,000 feet thick. Below that is lava, evidence that the coral grew on top of a volcanic peak. Since coral can only grow in shallow water, it seems highly probable that the top of the volcanic peak was at one time near the surface and that it sank at the same rate that the coral grew. Enewetak coral started growing some 60 million years ago and sank at the rate of 2 millimeters a century. Until recent years, few people could see how any real benefit could come from a study of the floor under the ocean basins. But already applications are beginning to appear. In naval operations, this knowledge is of primary interest to the submariner and to his adversary, the anti-submarine forces. At present, submarine operations are limited to the upper few hundred feet of ocean depth. Future submarines will almost certainly be able to go much deeper. They may be able to escape detection in rough terrain by lying quietly behind a peak or in a depression or canyon. Finding a submarine in these areas will require special sonar skills and meticulous interpretation of sound echoes. Sonar range can sometimes be extended by bouncing the sound from a hard, smooth bottom. The range that can be attained depends in part upon the slope, so both slope and bottom type must be known. A major objective of Navy geologists is to provide charts of the entire ocean bottom, showing details of depths, contours, bottom types, and slopes. Before that can be accomplished, much work must be done. The vast areas, great depths, tremendous pressures, all contribute toward the difficulties and cost of accumulating scientific data. In advancing the frontiers of any basic science, no one can predict the nature or scope of its practical applications. But from the information now available, there are few areas of research that show as much potential as marine geology, the study of the land beneath the sea.